give myself or David a shout, and we can see. Obviously, we're going to put everybody at the front, so we'll see how many spaces we've got. But definitely, we'll try and do that. So, and obviously, a big thanks from me, Caterina, for coming down to do this. So I'm going to pass over to you now.
Thank you very much. So I'm really honored to be here. It's probably the second time I speak to high school students in such a large crowd, so I'm a bit, sorry, never mind. That shows that I'm a little bit on the, the agitated side. No, but I'm really, really happy to be talking to you, and I thank you for the invitation and also for being here. So I had very vague instructions, and that's the way I like it, saying you can talk about something about particle physics, and this is, I'm talking about big data, big discoveries, and lessons that we learned and lessons that can be taught. Meaning that I'm going to have 5 talking points. This is not something that is totally structured, that we can think through and maybe develop during the panel. So this is my view. This is not a comprehensive overview of particle physics. It's just a starting point. So you can also ask me anything that you'd like. At this point in time, later in the coffee break, I'm not sure I can come to the drinks, via email, name.lastname @manchester.ac.uk. Really, there's no silly question. All right. So about me, I come from Italy. I passed through the UK for a PhD. I went to Geneva, Sweden, and Manchester during COVID. I like Manchester during COVID so much that I came back. Actually, it was from family reasons. And now I'm a professor at the University of Manchester. And I'm going to ask you something very difficult at this point. Please count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, what have we done here? So approximating your cross-section, which is the area that you're actually made of, that can be hit by particles, with a rectangle of 80 times 80 centimeters squared. This is what they did in Eurovision in 2013. You have just been traversed by at least 20 energetic fundamental particles from space. So the first talking point is that fundamental particles, or the particles that we cannot break any further, at least yet, are everywhere. You probably teach this kind of stuff, but I don't know if it's pervasive enough that, we have them everywhere. I mean, if we're talking about, dark matter particles and even exotic stuff, it could be just hitting us right now. And the other thing is that none of the particles that we deal with at the Large Hadron Collider, I'll talk about this later, are dangerous. So we respect all safety guidance and all that. So there's nothing dangerous about this. So what's matter made of? What are we made of? Well, it's the Lego idea. They're smaller pieces that constitute a nice, beautiful landscape. And this is what particle physics does. It breaks the components of matter by millions of little pieces. And what we study in particle physics is the smallest, the fundamental components of matter, not because they're more important than others, but because we can't break them any further. That's what fundamental means to us. And how do we create and study the smallest component of matter? Well, we need energy. We've talked about energy earlier. That was a really nice introduction. And where do we find this energy? And the answer is that it's all produced it's produced all over the place. This is essentially electricity. It goes into this big machine. This big machine is the Large Hadron Collider. It's a collider of protons. So there's 2 beams of protons that collide against each other. So you end up having proton-proton collisions that do boom and then do something. And that's something that they do is, you don't know. I mean, we have to guess it. And that's a beautiful thing about particle physics, that you put known matter as your input ingredients and you get anything out. So it could be like colliding, chickens and then you get ducks out. Don't do that. So anyway, that's the idea. So this is a really, really large machines because you need to accelerate these particles to a very, very high energy, and energy E equals mc squared, energy velocity, let's do all of that. It means that we're putting these particles to close to the speed of light. So we need the large machines. And what do we do when we have the collision? We look at the products of these collisions through different experiments. There's 4 of them. I'm working on one of them. And I'll show you a bit more about that. So just to give you a sense of dimensions, this is how large the Large Hadron Collider is. So if you put the center where we are, it would go out to Salford. So that's pretty large, I guess. And how big are the experiments that are looking at these particles? These are many buses worth. So you get into this place and you can't even see, well, it's all instrumented. So you just basically have a wall of electronics. So you don't see this nice thing, but it's really, really large. It's like 4 buses tall and 4 buses across. And in order to build these kind of things, you need really large amount of people and really large involvement. So how much is 13 teraelectron volt? So I forgot the biscuit here. These are the biscuits that I like. So this is a cute thing that you can tell the students. I always tell my students about it. So it's 51 calories for one of these biscuits. 1 calorie is 26 million teraelectron volt. Okay, so what's impressive about the Large Hadron Collider? It's 14. It's because a single proton's energy is 13 teraelectron volt. And if you convert that into calories, it's less than a biscuit. But there's 10 to the 9 protons in a bunch that collide, and they're concentrated in less than the diameter of a human hair because they're really tiny, so you need to really squeeze them in order to have something that collides. And out of this 10 to the 9 of protons, you get 60, 70, 80 that collide. Everything else just passes through. So this is the second talking point. In order to study the fundamental components of matter and to see what's beyond that, we'll get to that, we need huge international big science experiments. So one thing that we as educators, university and earlier on as well, we're doing is to inspire people, to inspire students and politicians also to join and support these endeavors, because we need this kind of big science to progress our understanding of what we're made of. So we've talked about LEGO. We are going to talk about the periodic table, and that's the inspiration for the standard model of particle physics. This is a model that describes all the particles, their interactions through the forces in nature. And the newest and not so new particle, because it's 10 years ago, and you probably heard about Peter Higgs passing. He was a great scientist from the United Kingdom. This is the last particle that was theorized in the 60s and then was discovered at CERN in 2012. So what does it do, this particle? It actually explains how we and the particles that we're made of get their mass. So you can think about this analogy. This is quite nice. I don't remember who it's from, but I'll add this link to the slides. It's like someone important gets into a room, and then everyone wants to talk to them. So this person that is walking into the room is one particle, and these other people are the Higgs field, and they concentrate around the person, the important person, the particle, and they make this person bulk up in mass, and they can't go as fast as they were going before, which means that they have gained mass. So this is the analogy that I think won some prizes also for explaining what this particle does and how it does it. So what's next? This is one of the many things that we're studying. This is especially what I study. It's dark matter. So what is dark matter? Well, it's dark. Right? There's no light that is emitted or absorbed by this kind of matter. But we know that it's there from astrophysical observation. It has mass, it feels the gravitational force, and we know that it's the main component of matter in the universe. So this is about 20% of the matter energy composition of the universe, and we're made of 5%. So there's 5 times as much dark matter as there is of dark energy, or sorry, not ordinary matter. Then dark energy is another story. But we're interested in this thing because it's matter. It could be particles. It does not belong to the standard model of particles that we know yet. So this is just a video that you can look at later on. Just click on the link and you see the path of the protons to create from known matter, unknown matter. How does it work? How do experiments see it? You can look at it later. And this is just what I do in picture. So it's, do I go and look at the particles myself? Do I look at the microscope? No, actually, I use computers and use data mostly. So this is an interesting plot because it tells you on the y-axis the size of the data set that we're looking at, and just the size of the ball, basically. It's the amount of data that we're in principle taking into account. So you're looking at the emails, Netflix or YouTube or Amazon, And these are all balls, but then the ball for the amount of data that we generate from the collisions of this particle collider is the largest of them all at the moment. So what we have to do is process this data and get some insight out of it. So this is what I do. I look for dark matter in the process, through processing this data with the algorithms. And we use advanced, I call them real-time data analysis techniques. That's my specialization. It's just trying to get insight as fast as you can from when the collision is derived. So it means that you have to not only program on normal computers, you have to program on electronics, you have to program on accelerating, like GPUs, like this. Now everyone knows what the GPU is because everyone has it in their computers, a gaming card, essentially. So there's a lot of techniques that include artificial intelligence, and also we shared a lot of tools with industry. So this is the third talking point. We need a lot of efficient data analysis, including AI, to process all this data from the LHC into insights on what we know and what we don't know yet. And efficiency at this point doesn't just mean, oh, let's make this faster. It also means let's spend less energy doing this, because that's something that we are actually concerned about as citizens of the Earth. So there's a lot of sustainability efforts that are ongoing from the computing, but also for the particle accelerator side. So the last couple of points are about the Atlas collaboration and what it is to be one of 3,000 people that all work for the same cause. So this is a picture in 2010. Only 1/10 of the people that are working on this experiment are there. You can find me in the middle somewhere. And so far, we've published more than 1,000 open access papers on scientific results. And each paper has all the 3,000 people as an author list. So you can see the author list there. It's really long. These are like 10 pages of, it's longer than the article sometimes. But this is to prove that there are so many people involved, so many countries, so many funding agencies involved, because it's 42 countries, 200 universities, and more than 1,000 students that are actually running the show. So you think, okay, there's a lot of people here. What is going back to society? And I think I would like to divide in 2 points. The first point is what Fabiola Gianotti said a few years, I think it was Davos, that is, these places where you do global research are important because people from around the world come together to show what can be achieved when people overcome their differences to work towards common goals. So in the current political and foreign relations climate, this is quite important to bring forward. And the other thing is that, kind of following from this, the UK has the most teachers attending the teaching programs. And if you're interested to do something like this, because there are teacher programs, there are visits to schools, and et cetera, and just email me and I'll find the right person that can talk to you, and you can either visit CERN or go have training there. There's a lot that is done to bring CERN to schools and to students. And the other thing is the value of basic research. So you want to think, okay, I'm putting all this money to build this machine. What do I get back? And mostly it's skills and training. And that then in turn increases the gross internal product. So if you want to think about money. So there's a lot of different reports about this if you want to read. So this talking point is particle physics research is collaborative, open, and open source, but also provides economic and societal benefits. One thing, if you want, we can talk about in the panel is how do you combine the commercial interest of a company that is using an algorithm and you wanting to make this algorithm public for everyone? And we have answers for that, I'd say. Last talking point, demographics. And this is something that really teachers are, I think, extremely important in carrying forward is the left plot is the total number of authors and the number of women authoring Atlas papers over the years. So it grows. It started from 10% in 2004, and now it's about 20%. So this is the number of women that there are there. But it's not just women, it's about minorities in general. And this is something that happens in STEM, that 27% of the STEM workforce is female. STEM workers tend to be younger rather than older, what happens after. And only 12% of the STEM workforce are from ethnic minorities. And only 10% have a disability. So how can we bolster the numbers here so that we make our work environment more diverse? Because it's been proven that this is better for research itself. So this is the last talking point. Oops, too far. So with your help, I think we can amplify the voices of underrepresented minorities in high energy physics and STEM and show that this is possible. It's possible to be a person that is not, an average person, I guess. Let's look at that. And does this kind of things, because this is one of the ways to help make our work environment more diverse. And regarding work environment and work environment in the classroom, it's very obvious that students who are educated in a diverse and respectable work environment can carry it forward for the further steps of their career. So that's basically it. So thanks a lot for your attention, and I'm happy to take any questions now later in the coffee break.
Round of applause. Right, so I think questions during the coffee break. So, Caterina, you're going to be here for a little. Oh, is there a question from the room? Oh, everyone's scared now. Okay, right. So we have got a 10-minute coffee break. 12 minutes. But there's plenty more after this, including the panel. So do be back by about 20 to 25 past. Thank you.